rational functions. So our ultimate goal is going to be to graph rational functions without a calculator. And again, as we've seen with a few other topics so far in this class, you can get away with using your calculator to do the homework, and I won't have any clue. However, the test questions are designed so that you can't use a calculator, so that you have to be able to do it without a calculator. So for your own benefit, it's a better idea not to use your calculator. And I don't mean don't use your calculator to do calculations. I mean don't use your calculator to graph the function and then trace it when I ask you to graph a function. So I'm not saying don't use your calculator at all for anything. I'm just saying we're going to talk about how to find all the characteristics of these graphs algebraically and use those to graph the function by hand. And so you want to practice those skills as opposed to just plugging the function into your calculator and tracing the graph. Because on the test, we'll mostly be finding all those characteristics algebraically, and the graph is just kind of a result of that. So you won't be able to use just your calculator to graph it. So today we're just going to focus on finding those characteristics and how the function behaves, and then tomorrow we'll put all of that together to actually sketch the graphs. But let's start by looking at the graph of a rational function so we can get an idea of just kind of how they look and what properties they have. So here we have a rational function. This is f of x equals x squared minus 3 over x squared minus 4x. So when we talk about functions and their graphs kind of in general, we think about four main things. The first is the x-intercept, the second is the y-intercept, right? And we've already talked about how finding the x-intercept and the y-intercept of a function is exactly the same no matter what type of function it is, right? How do you find the x-intercept of a function? For y or for x? Yeah, so our y value is 0 on the x-axis, so we set our output equal to 0 and solve for x. So we're solving our output equals 0. So we're taking our function, setting it equal to 0. To find the y-intercept, what do we do? So if we're on the y-axis, what do we know? So our y-coordinate, these points right here, have a y-coordinate of 0. Those are our x-intercepts. So our y-intercepts are going to have an x-coordinate of 0, right? So because we haven't gone left or right. And so our horizontal movement is 0. And so we are evaluating f of 0. And again, those are the same no matter what function we're working with. So you don't have to try to, especially with rational functions, I feel like students tend to try to, think of it, as its own little thing. How do I do this for a rational function? Whereas these things are the same no matter what function you're talking about. And then one of the other things we think about when we think about the way a graph behaves or a way a function behaves is the domain, right? We always want to look at what x values we can plug into the function and correspond to points on our graph. So when we think about the domain of a rational function, one thing that we notice as we look at the graph is that there's these x values. Do it like this. that my graph never actually reaches. It's a little hard to tell for that one because it gets really, really, really close. But notice that my graph doesn't actually cross the y-axis ever. And so we just get infinitely close to the y-axis, but we never actually reach it. So we don't have a point that corresponds to x equals 0, which makes sense if we think about this as a rational function, because what would happen if I plugged 0 in there?
It wouldn't work.
Why?
Because if you were to solve out the bottom, you get 0, you can't have 0.
Right, we can't divide by 0, right? So if we plugged x in, or sorry, x equals 0 in, we would end up with something divided by 0, which is impossible, which tells us that this function is not defined for x equals 0. So we've done this before. We found the domain of rational functions, right, by setting that denominator equal to 0. What that corresponds to on a graph is what we call a vertical asymptote. So it's a vertical line that my graph approaches but never actually hits. So that means that my function is going to just get closer and closer, or get bigger and bigger and bigger, or smaller and smaller and smaller as it approaches that number. So in this case, we have two of them. We have one where x is equal to 0, and then we have another one where x is equal to 4. And that one's a little bit easier to see that it never actually touches that vertical line. And you can see in the denominator, if we were to factor that denominator and set it equal to 0, we would get 4 and 0 as our solutions. So those are the values that are not in our domain, and also the values that give us our vertical asymptotes. So those two things are the same thing. Our vertical asymptotes occur where the function is not defined. Because if there's an x value that's not in the domain of a function, then there can't be a point on the graph that has that x value, right? So this is kind of bringing together what we've done with graphs as far as like finding the domain and range, and what we've done with the functions themselves as far as like setting those denominators equal to 0 and finding the x values that aren't there. So vertical asymptotes these occur where the function is undefined. Also known as where the denominator equals 0. So all that stuff we've done to find domains of rational functions really helps us here, because we use the same process to find where our vertical asymptotes are. Our vertical asymptotes are horizontal lines. No, they're not. They're vertical lines. I'm sorry. They're vertical lines, so you want to remember that like when you give a vertical asymptote, it has to be the equation of a vertical line. So you always write these as equations. So in this case, we have a vertical asymptote of x equals 0, which is the equation of the vertical line that has all the points with an x value of 0, and then we have a vertical asymptote of x equals 4. So we can't just say the vertical asymptotes are 0 and 4, because they're not numbers, right? They're actually lines. And this is pretty important. Like, I know I always harp on notation, and sometimes it's eye-rolly, but it's really important with graphing these guys, because we solve for x when we find the x-intercepts. We also solve for x when we find the vertical asymptotes, right? There's a lot of things going on as far as different x values and different y values. So that notation is going to help us remember what those objects actually are, right? When we have a point, it's an ordered pair. When we have an asymptote, it's a line, so it's written as a line. And so that's going to help us. The notation, or how we write it, is just going to help us to actually figure out what it looks like on the graph. So the last thing that we think about when we think about graphs should number these maybe. 1, 2, 3. Is we think about what's called end behavior. And end behavior is how the function behaves when my x values get really, 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 really big or really, 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 really negative. So in terms of a graph, it's like what happens at the right arrow and what happens at the left arrow. So as I'm coming out here and as I'm moving in that direction. So this is how the function, so the y values, because those are the values of the function, behaves as x approaches negative infinity and as x approaches positive infinity. So this is notation that you'll see quite a bit, especially when you take calculus, that idea that your x or your y value is approaching something. So when we do that little arrow, we're just saying that x is getting really, really, really negative or x is getting really, really, really positive. So humongous numbers. So when it comes to rational functions, often a specific thing happens. Where do I want to do this? For our end behavior, notice that on the left side, the graph is kind of coming up and leveling off at a y value of 1. And on the right side, the function is coming down and kind of leveling off at a y value of 1. Right? So we don't actually see it touch the y value of 1 because it never does on the ends. One thing that we have to remember about this is horizontal asymptotes, which is what we've just drawn, a horizontal line that we approach but never actually reach. And vertical asymptotes are slightly different in that horizontal asymptotes only have to do with end behavior. So what's happening in here doesn't really matter. It only deals with the very left and right side, which is why it's totally okay that my graph crosses y equals 1 in the interior of the graph. All we're talking about when we talk about horizontal asymptotes is a specific value that our y values approach on the right side and on the left side. So here, whoops, that's the eraser, here and here.
So how this is different than like listing it as domain and range, where you give like it's just in relation to the y-axis where it's located.
Yeah, so we could give, if I looked at this graph and I gave the range would be negative infinity to positive infinity, right? Because over here at x equals 4, the function goes all the way down to negative infinity. And at x equals 0, it goes all the way up to positive infinity. So giving the range doesn't give me an idea of what happens on the ends, right? So I could give the range, and if I just told you the range is negative infinity to positive infinity, we wouldn't have any idea that as x gets really, really big, my y values approach 1. So it's kind of a little bit more specific than just the domain and range. And the reason that that's important with rational functions is, as you can see, there's sort of like multiple pieces to a rational function. So just giving the domain and range doesn't necessarily tell us how those x and y values are situated on the graph. Does that make sense? So when we look at horizontal asymptotes, this is a specific y value that the function approaches on the left and right edges of the graph. So because horizontal asymptotes are related to end behavior, they only relate to what's happening on those edges. So when you look at the right arrow, where is it going? And when you look at the left arrow, where is it going? So we have some generalizations as far as finding the horizontal asymptote. There's 3 possibilities, and we'll sum them up in really short generalizations that you can kind of just memorize, but I think it's a good idea to get an idea of where those come from. So let's look at the 3 possibilities in more detail, and then we'll kind of sum them up. So the first possibility is when we have a rational function, it's always a polynomial divided by a polynomial, right? And every polynomial has a degree. So the first possibility is that the degree of the numerator, and remember degree with a polynomial in one variable is just the biggest exponent.
Is this under the horizontal asymptote?
Yeah, I would maybe do this part like elsewhere because we're going to do a shorter summary in here, which you can refer back to a little bit more easily than sorting through everything we're about to do. Numerator. So the degree of the numerator can be bigger than the degree of the denominator. So for example, let's say f of x equals 5x, well, no, let's not do that. Let's do x to the 4th plus 3x to the 3rd minus x plus 1 over x squared minus 6. So notice the degree of the numerator is 4 and the degree of the denominator is 2. So the degree of my numerator is definitely bigger. When we talked about degree originally, so I mean, like, we defined this thing called degree, like who really cares, right? The reason that we care about degree is because of end behavior. So when x gets really, 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 really big, for instance, if x was like 10 billion, then x to the 4th is 10 billion times bigger than x to the 3rd, right? Because you multiply x to the 3rd by x to get x to the 4th. Which means that like that 3x to the 3rd minus x plus 1 is like negligible when x is really, really big. It's like rounding 60 billion and 1 cent to $60 billion. Those 3 terms at the end of the numerator just become so small in comparison to that first term that we can kind of just round them away. And so we say as x approaches either positive or negative infinity, f of x approaches, I'm just going to like round the numerator and denominator, so to speak, right? So I'm going to say, okay, my x value is so big that x to the 4th is like billions of times bigger than x to the 3rd. So x to the 3rd is like really tiny in comparison. So basically this is going to behave like x to the 4th in the numerator, and it's going to behave like x squared in the denominator. If that's upsetting to you, think about this. Do you guys agree with me that that is basically the same?
Right. Oh, it's not.
I totally put this one in the wrong place. Big numbers, 70. There we go.
Oh, it was not right either.
Why not? Oh, because I skipped. I did the same exact thing, didn't I? 1, 2, 3. There we go. You guys agree that's true? That's what I'm doing when I drop that 3x to the third minus x plus 1. Is that x to the fourth is just so darn big that everything else is like negligible. Yes?
You just take like the biggest
Mhm.
degree minus the over the smallest degree.
You take the leading coefficient
Of
of each one. Yep.
So even if like x is 10, for instance, would
Uh-huh.
this be applicable?
No. This is only applicable as we approach infinity and negative infinity. So that's why we say as x approaches negative infinity, so, or positive or negative infinity, we are not saying that that function is equal to x to the fourth over x squared. We're just saying that when x gets really, really, really big, that function behaves in the same way as x to the fourth over x squared.
So you're just like
Yeah. Good. This simplifies to x squared. And what happens to x squared when x gets really, really big? If you plug bigger and bigger numbers into that, if you square bigger and bigger numbers, what do you get? Bigger and bigger numbers, right? So as x approaches plus or minus infinity, f of x approaches infinity. In this case, it can't approach negative infinity because x squared is always positive, right? So as we move to the left and the right on the graph, our y values just get bigger and bigger and bigger. So this is going to look something like, maybe like, that. So remember, rational functions often have more than one piece. So in this case, this is like a vertical asymptote, right? And there is no horizontal asymptote, right? Because there is, if I move to the left, so if I look at the left-facing arrow, it's just going off to infinity. It's not approaching a specific y value. And same thing on the right. If I follow that arrow to the right, it's not approaching any specific y value. So in this case, we say there is no horizontal asymptote. It is possible for these to have what's called an oblique asymptote or a slant asymptote, and the only reason I mention that is that the homework problems like have multiple parts, and one of the parts asks about an oblique asymptote. None of the ones I give you are going to have them, so every time you see that question, you just say there isn't one and like move past it because we're not doing those in this class. But I couldn't get rid of like that one part of the problem. So going back to our list here, our first possibility is that the degree of the numerator is bigger than the degree of the denominator, and that results in there not being a horizontal asymptote every single time. No matter what the function is, if the degree of the top is bigger than the degree of the bottom, then it's going to like go off to infinity or go off to negative infinity on the right and the left. Okay, second possibility. Well, I suppose the degree of the numerator could be equal to the degree of the denominator. So for example, let's do like f of x equals 6x squared minus 3x plus 2 over 3x squared plus 5. So looking at our leading coefficients, right, which give us our degrees, we have degree 2 and degree 2. So the degrees are the same, which means that as x approaches positive or negative infinity, and again, as x gets really, really big or really, really negative, those last few terms, so all the terms except the leading term, become negligible. They just become so small in comparison to the leading term that we can just kind of pretend they're not there. Just like we're rounding. So our function is going to approach 6x squared over 3x squared, which is equal to what? 2, right? Our variables cancel, and then 6 divided by 3 is 2. So as x gets really, really big or really, really negative, so as we follow the arrow to the right or the arrow to the left, my function, my y value, approaches 2, which is exactly what it means to have a horizontal asymptote, is that as you move to the right and left, your y value approaches a specific number. So our horizontal asymptote is y equals 2, which in more general terms is the ratio of my leading coefficients. Right? I just divided the leading coefficient of the numerator by the leading coefficient of the denominator. So the ratio of leading coefficients. I'm going to make it fit. So what that would look like on a graph is I'd have this horizontal asymptote right here where x is equal to 2. I'm sorry, where y is equal to 2. And I may or may not have a vertical asymptote somewhere. And then my function would do something like this and that. So that right arrow gets closer and closer to that horizontal line, and the left arrow gets closer and closer to the horizontal line as we move out to the edges of the graph.
How do you know this, like, that the graph looks like that?
Well, that's just an example of how the graph could look. I mean, that's not the graph of like this necessarily. It's just basically what it might look like. So notice in our example that we started with that the degree of the numerator is the same as the degree of the denominator. So what should my horizontal asymptote be? Y equals 1, right? Because both of those have a leading coefficient of 1, right? That's 1x squared and 1x squared. So 1 divided by 1 is 1. And that's what we found when we looked at it graphically, right? That as my arrow goes to the right, it approaches a y value of 1, and same as my arrow goes to the left. So if the degree of the numerator is equal to the degree of the denominator, my horizontal asymptote is y equals the ratio of, I don't need this guy anymore, the leading coefficients. And again, just like with the vertical asymptote, you want to be careful to always give that as the equation of a line. So it's y equals some number. Okay, there's one more possibility, which is that the degree of the numerator is smaller than the degree of the denominator. So for example, f of x equals 6x minus 4 over x squared plus 3x plus 1. So the degree of my numerator is 1, and the degree of my denominator is 2. So I see that the degree of the numerator is smaller than the degree of the denominator. And as x approaches plus or minus infinity, again, we do the same thing. So I'm going to give you all these generalizations, which you can definitely just memorize to always do this. However, if you just follow this process of looking at the ratio of the leading coefficients, you can always reach the same conclusion as you would if you just memorized the generalizations. So because we did the same thing on all of these, right? We just looked at the ratio of those leading coefficients. So these guys. And that's how we figured out what our horizontal asymptote was, or if it had one. So same thing down here. As my x value gets really, really big or really, really negative, so as my graph moves to the right or left edges, f of x is going to approach, so my y value will approach 6x over x squared, which simplifies to 6 over x. What happens to 6 divided by x as x gets bigger and bigger and bigger and bigger? So if you take a single number, so like 6 pizzas, and you start dividing those pizzas into more and more pieces, what happens to the size of each piece? It gets smaller and smaller and smaller, right? If you divide a constant amount into more and more and more groups, each group contains less and less. So this number, 6 over x, is just going to approach 0, right? It's going to get smaller and smaller. If we cut those pizzas into more and more pieces, eventually, like, we're all just going to get like this tiny sliver, like basically no pizza, right? So as x approaches plus or minus infinity, f of x, so the output of our function, or our y value, approaches 0. Which means that our horizontal asymptote is y equals 0. So very similar to that second case, except here it's just always y equals 0. We don't have to worry about the coefficients or anything because that bottom is always going to outweigh the top. So it's always just going to go to 0. So that's going to look graphically something like, stay away from that watermark, something like, for instance, the graph of 1 over x. looks like this. So my right arrow gets closer and closer and closer to y equals 0, and my left arrow gets closer and closer and closer to y equals 0. So I have that horizontal asymptote here at y equals 0. So generalizing, if the degree of my numerator is less than the degree of my denominator, then my horizontal asymptote is always y equals 0. So this kind of summary here at the bottom, if you want to just memorize that instead of going through the whole process of taking the ratio of your leading terms, that's probably the quickest way to do this, is just get in that habit of being like, oh, the top outweighs the bottom, or the bottom outweighs the top, or they're the same. And that'll always get you to your horizontal asymptote. So let's do one example where we find all our asymptotes. Today in your homework, you're not graphing anything, you're just finding these individual components, and then tomorrow we'll put it all together to actually create a graph. Oh, of course. Here?
Yeah.
And one thing to remember with these rational functions is that, like, they look pretty complex, but 1, 2, and 3 you guys have been doing since the very beginning of the semester, right? You've been finding x and y intercepts just with different types of functions, and you've been finding the domain of rational functions since like day 3, right? Finding where the denominator is 0. So really, even though this looks like a lot, that horizontal asymptote is really sort of the only new part of it as far as things that we already know how to do. It's just kind of putting it all together in a different way. So let's look at g of x equals 9. No, let's make this kind of simple. Let's do x squared minus 9 over x squared minus 6x plus 8. So the first thing I always do when I'm graphing rational functions or really doing anything with rational functions is I just factor the numerator and denominator, because we'll find that sometimes it's convenient to have it in factored form and sometimes it's convenient to have it in expanded form. So if I just write them both at the top, I don't have to like factor every single time I want it to be factored. So this is x plus 3 times x minus 3 over x minus 4 times x minus 2. So let's start by finding the vertical asymptotes. And along with that, I'm going to find the domain of the function, because those are related, right? The vertical asymptote occurs at the x values for which the function is not defined, which are the values that are not in my domain. So to find my vertical asymptotes, we always solve the equation denominator equals 0, because vertical asymptotes exist where the function is not defined. So if we set our denominator equal to 0, we get x equals 4 and 2. I'm not going to leave it like that, though, because my vertical asymptotes aren't numbers, they're equations, right? So I'm going to write 2 individual equations. X equals 4 and x equals 2. So that's two separate vertical lines. And those lines, we draw them as dotted lines because they're not part of our function. Like the points on those lines aren't points that correlate to our function. It's just like a boundary, kind of like when we were doing those piecewise functions. It's like a fence that we never get to touch. You can kind of pretend it's like one of them electric fences. We can get really, really close, but we can't ever touch it. So, and then what we just did there actually found our domain as well, because the numbers that are not in the domain are the numbers that make the denominator 0, right? So we can say that we already know that x cannot be equal to 4 or 2, which looks a little weird because over here I said x is equal to 4 and 2, and over here I said x is not equal to 4 and 2. But again, that correlates to the fact that my vertical asymptotes aren't actually points on my function, right? These are the lines that tell me what x cannot be on my function, so the x values that do not correlate to points on my function. So my domain is going to be negative infinity to 2, 2 to 4, and 4 to infinity. Just